I set up the coding challenge in the last video to add up the first 100 numbers. So 1 plus 2 plus 3 plus 4 all the way up to 100, and we should get a final result of 5050. Now we're going to use this equation here. The first thing we have to think about is, are we going to represent the numbers in integer form or in our fixed point number system, or are we going to try and mix and match a bit? So the first thing to note here is that if we're adding up the first 100 terms, then we would have, for example, 100, which is the value of n, divided by 2. So when we go through this division and n is an even number, then we're going to get an integer value, and it's going to be exact. So there isn't any rounding issue. So we could generate the result for adding up the first 100 terms simply by ensuring that we use integer values for our a, our n and our d, and it would be quite a straightforward process. And if you want, you can go ahead and build that and you can generate it and you can see it working. But I thought I would go ahead and try and generate something just a little bit more general, and then you can see the kind of trade-offs I have to work with. So the first thing to note here is that if the value for n here wasn't an even number, so if it was like sort of, if the n was 3, whenever we go through the division we'll have 3 divided by 2, which is going to be, if we did it with integer division, we'd have the value of 1 and it would have a remainder 1. Okay, so we wouldn't get the number 1.5, so it would be an approximation. So looking at that, I thought, well, I don't think I'll bother using the integer values. I think I'll use all fixed point values so we can get exact results. And we can make the coding challenge just a little bit more general. So rather than implementing just this, being able to implement only the integer values, therefore it would only be exact for values for n which are even, I thought I would generate it so that it would be accurate for all of the values, whether the n is even or odd. Now there's a problem with that, in that if we were to use our fixed point number system, then we can only generate numbers up to plus 128 and minus 127. So we're not going to be able to get the answer 5050 because in our small machine at the moment, our number system doesn't go up to these values. It'll be different whenever we employ our floating point unit, but for the moment this is what we have to deal with. So we're just going to change the coding challenge slightly. So I'm just going to add up the first 10 terms. So let's crack on and we'll see the actual code. So we're going to now use a fixed point and we're going to add up just the first 10 terms. Now we'll go down here and we'll see my solution. Now it's not necessarily the solution that you may well have come up with, and I've decided to go about this in a slightly different way from my previous code that I have written. I decided I wanted to predominantly use the stack in order to generate this little mathematical equation. Where is it? Oh, yes, to generate this little mathematical equation. And it's not something I've done previously, so let's have a look and we'll see exactly how I have gone about it. So I started off with origin 0 cross 8000. Now let's just ignore the actual code. So this is the code here. Okay, so it's not very long, it's 20 or so lines long. Now the very next thing I did was I went down to the start address. So I said start address 0 cross 8500. Okay, so that's where we're going to place all of our variables and our data. Now we know we're going to have 3 values going in. We're going to have the a, which is the first term, the n, which is the number of terms, and the d, which is the difference. And each one of these are going to be fixed point numbers. So we can define them here. So the first one is going to be the value of 1, so it has to be hash f1.0. The next one is going to be the number of terms, which is 10, and the final one is the difference, which is a value of 1. And we're going to store the answer in this memory location here called ANS. So I've done DS, and we set aside one memory location for the answer. Now we know we're going to have to do a fixed point multiplication and a fixed point division. So I've got the address here of the subroutines for both of these. So remember, these subroutines are actually in the ROM, and we have to go in and find them. And this tells us where we are going to find these subroutines. And finally, I've put a little note at the bottom. We're going to add up 1 plus 2 plus 3 all the way up to 10. So that's going to give us the number 55. So we're going to check and see whether what is the correct fixed point value for this. So again, within if you've got the actual course and you're running this course, you'll have access to this other little bit of code here that's called float to hex. Okay, so if we click on that, and we can go run without debugging. Now you might not see this because it goes off the bottom of the screen, but I'll bring it up here hopefully so you can see it a little bit further. So you can see here that we can put a floating an actual decimal value in. So the correct answer for this here was the value of 55. So if I put in 55 return, you'll see it converts it into our 8.8 fixed point number. So the correct answer we should get is 0 cross 3700. Okay, so this is the number 55. So we want to remember this 0 cross 3700. That should be the final answer. Okay, so we go back into the code here, and we'll actually talk through how I've generated the code. Now again, it's maybe not the quickest method. We can change this around a bit so that it will work a little bit faster, but I just wanted to get something up and running. So the first thing we're going to do here is we're going to generate the n-1. So we're going to push the value of -1 onto the stack, and then we're going to push the value of n. And notice I put n in the little brackets because it's going to go down here. It's going to find the memory location n, but we don't want to push the memory location. We want to push the value within the memory location, which is the number 10. So if we put the brackets round about it, it will push the actual contents of that memory location. So now we've got both of these sitting on the stack. Then we can pop the first one off, which is going to be the n, and then pop the next one off, which is going to be -1. And once we've popped those off into register R0 and R1, we can simply add both of them together. So we add R0, R1, so R1 becomes the value n-1. And then we can push this value n-1 back onto the stack, and then we can push the value of d. So again, the value of d, we come down here, is the value of 1. So we're going to do the multiplication here. So it's going to be, we're going to finish up with R0 is n-1 times d. So we've pushed both of those on. We've jumped to the fixed point multiplication routine, and we've popped the answer off back into register R0. So R0 has now got n-1 times d. And then we can push the number 2 onto the stack. We can push the value a onto the stack, and then we can go to the multiplication, and then we can pop the result off. So this result in register R1 will be the value 2 times a. And then we can add the register R0 and register R1, which will add the 2a and the n-1 times d. So we've got this value here in register R1. We can then push the value of n onto the stack, and we can push the contents of register R1, which is this here. So we're going to then multiply together the n and the 2a plus n minus 1 times d. And finally, we can push this value R0, and we can push the value of 2, and we can do the division. So now we're going to divide the whole thing by 2. So we're going to take what we have up here and divide it by the number 2. And we pop the answer into register R0. So the final answer sits in register R0, and we can clear off register R1 just so we don't get confused about where the answer sits. And then finally we can store the final answer in the memory location given by ANS for answer, which is this memory location here. Okay, so finally we can end the program. So that's my little piece of code, and it's the first time I've gone in and used the push and pop prevalently, completely within the code. Now the nice thing about doing it like this is that I don't have to bother about saving intermediate values in registers, or saving intermediate values in memory locations and then getting them again. You'll notice here that we are able to generate this little equation here simply by using register R0 and R1. And in fact, we could generate a whole multitude of really complicated equations by using very few registers, using this stack method in order to generate these equations. So that's enough of me talking. Let me I went into, let's have a look and see, terminal, run, assemble file. Now you can't see it here because it's gone off the bottom of the screen. Maybe if I bring it up here, but you can see it says assembly successful. Okay, so let's load it into the machine and let's see it running and see if it gives us 0x3700. So let's load the actual code in. So I go into the computer, into the RAM, and I find the file. So this is the file here. I press open, close that, and now the program is in the RAM. So let me run up the program and actually get it running. So that's the computer now running, and you can see everything is pulsing away nicely here, and the microcoded ROM is generating all of the sets and the enables. So let me fast forward this to the final result. It takes approximately 1 minute to run. So here we have our answer in register R0 3700, which is the correct answer. And if we drop down into the machine, you'll see that within the RAM at that memory location here, we have the answer as well, 3700. So that's our very first coding challenge. I will set some other coding challenges, and at the end of the week I'll generate a solution and I'll put the solution online. But it's a good thing to try it out for yourself, because there's lots of different ways of programming this machine. So thank you for listening. I'll get you on the next video. Goodbye.